Welcome to a podcast on thermodynamics. This is a basic overview of everything that we've learned in class, and it should help you review for your test. So, thermodynamics is the study of heat and transfer of energy, heat and temperature, calorimetry, and you have another video you can watch on that. But let's look and see some basic vocabulary words. Enthalpy, there's an H right in enthalpy, and enthalpy actually has the letter H as the symbol for it. And so how convenient that enthalpy, or H, is the heat in a reaction. And so when I spell enthalpy, I actually write it with a capital H right here. And so the heat of the reaction is actually what you already know as endo and exothermic. And so if I look at both of these diagrams right here, in diagram number 1, I have a system and surroundings, as I do in diagram number 2. And a system would be a beaker, you, a rocket ship, plant growing. And so the system in this case is losing energy to its surroundings. If you felt this beaker, the system, it would actually feel hot to the touch. And so therefore it is called an exothermic system. And in an exothermic system, the energy in here is going down. The difference actually inside is a negative value because it is losing energy to surroundings and the surroundings are increasing in their energy. So delta H in an exothermic reaction, heat is exiting the system and so it's a negative value, or, it means that it is less than 0 because it's a negative number. Now in this case over here, this is an endothermic system, and you have experience with this because you've had an ice pack before perhaps that you've hurt yourself in a sport. You snap it and it feels cold to the touch. So when the chemical reaction takes place, it is actually gathering heat from the surroundings to make it work. The surroundings are going down in energy and the system is actually going up. And so therefore delta H is positive because the system is increasing in energy. Heat is entering it. So, energy is entering it. And so therefore, delta H is positive, and delta H in this case is greater than 0, because positive numbers are greater than 0. You need to get that in your head, and we'll look at a graph in a second here, a potential energy diagram, to help you out even more. So, endothermic and exothermic. This black arrow in this endothermic graph is actually got a special name. It's called activation energy. And you know that from before. If you don't, now you remember it. So where would you draw an activation energy arrow in this diagram over here? In the exothermic graph. I will put it right. Oops, I just moved that. I will put it right here. That's an exothermic activation energy arrow. Now if you notice, in the endothermic reaction, what's true? There's more energy going in than is coming out. The reactants are here and the products are here. What's true in the exothermic graph? The reactants are here and the products are here, but there's more energy coming out than's going in. That's why it's called an exothermic reaction. And if you look at the difference between the reactants and the products, so here's the reactants and here's the products. If you did final minus initial, you would actually come up with a negative value, which makes sense. So this is my delta H, right? I'm going in a negative direction from where I start from, and so it's a negative value, and so exothermic has a delta H that's negative, or it's less than 0. Now let's look at endothermic, and what is true? What's true about my final minus my initial? The delta H here is going in a positive direction, right? And so delta H in this case, because I end up higher than where I start with, is a positive number, and delta H is greater than 0. Alright, now moving on, let's talk about what a catalyst does to an, and I gotta look back, sorry, real quick, so I'll do it the same way, okay, to an endothermic graph. So this is endothermic, and this is exothermic. What's a catalyst do? Well, a catalyst simply is like a translator. It takes the reactants and the products, doesn't do a thing to them, but it makes what happens behind this hill a lot easier. So it actually lowers this hill. So as to come in, I can actually erase this part. And so what did it change? It didn't change the reactants and the products, did it? Right? It just changes activation energy. The activation energy used to be higher because the hill used to be up here. So my reactants and my products do not change. My reactants and my products do not change. What happened? The hill used to be here. Here's where it is now. And so my activation energy went from that high to that high. And went from that high to that high. And so it makes it easier for it to happen. So all catalysts do are they lower the activation energy. That's it. They make it easier for it to happen, for the reaction to happen. Now, there's another word called entropy, and there's a big R right here. Okay? That R means randomness. And the letter for entropy is not R, it's S. So guess what? Randomness ends in S, and so entropy's letter that goes along with it is S. For enthalpy it was H, for entropy it's S. Now, I like the fact that there's two S's in randomness because there's two things to remember, states of matter and number of moles. Now on this number line, these are states of matter, solid, liquid, aqueous, and gas. And I'm going to say that this number line is just like a number line you have in math, where solids are more negative, they are super duper ordered, okay? And as you move along this number line from solids, which are packed and very organized, to liquids, which are more like a square dance, to aqueous, which is like putting big boulders in the middle that float around, or noodles and pool noodles in between all those square dancers in a pool, and the gas, which is absolutely crazy because now they're on a trampoline. The system is going from orderly to less order. Just like a number line going from negative to positive, or less random to more random. And you need to memorize this number line, or letter line, and you're going to use it. So let's use it right now. So, for example, what if they have an entropy example where they say predict the sign? Well, let's predict the sign for this first equation. So for this first equation right here, and here's equation number 2. So for this first equation, what do I have? Look at my states of matter. They're all gases, so they're not changing. What is changing? In my reactants, I have 2 moles and 1 mole. That's a total of 3 reactant moles. How about my products? I have 2. So I'm going from 3 moles of reactants to 2 moles of products. Sure looks like it's getting more orderly to me. And so the sign on our number line, remember from before, this is more ordered and this is less ordered. This looks to me like it's going in a negative direction. So the sign for this that I would predict for S is a negative sign because it's becoming more orderly. Now, let's look at sodium chloride. I have a solid and I have a liquid. I have 1 mole and I have 1 mole. My reactants and products are not changing in terms of moles, but my states of matter are. I'm going from a solid reactant to a liquid product. And if you think of your letter line, what's happening? I'm starting out from a solid and I'm ending up with a liquid. I'm going in this direction. And so I would predict the sign for this to be positive. So there's prediction problems, and then there's actually, can you do the math? So, to do this, I need to actually have some values that are not listed on this table, and the values that are listed in a book or a chart for this, I'm going to go ahead and fill in. So what I need to do, sorry about that. What I need to do is I need to follow this equation to find delta S for this reaction, which is entropy. I need to do sum of the moles of the products minus sum of the moles of the reactants, or final minus initial. All right? And so to do that, I'm going to go ahead and put 2 moles of SO2 plus 2 moles of NiO. And what I just do, all I do is copy down those products and put them over here. Okay, now, I'm not filling in any numbers yet. Let's go over to the reactants, and I have 2 moles of NiS plus 3 moles of O2. And that's my basis for my math. Now I'm actually going to go and fill in number values that I get off a chart. Often they give them to me in a problem. And for SO2, that is 248. And the units for S, which we'll go into later, are joules per Kelvin mole. Since I have 2 of them, I'm going to multiply. Plus, right? Okay, so this is like a little mini set inside this bracket. I have 2 moles of NiO, and I'm going to go ahead and take, this is 38 joules per Kelvin mole. Now if I was to stop and do my math right now, I would get 496 for this, and I would get 76 for this. Now, those get added together. Meanwhile, I look up my values for this other part, and for NiS, nickel sulfide, nickel 2 sulfide, my value would be 53 joules per Kelvin mole. Again, I'm not making these up, I'm getting these out of a chart. They're known values. And you multiply those by 2. And that's a little mini bracket inside here. And now I need to look at my value for oxygen. My value for oxygen is 205 joules per Kelvin mole. And since I have 3 of these, I multiply 3 times 205. And my numbers for this are 106 plus 615. Now, what's going to happen is I'm going to go ahead and subtract these. So this whole number, whatever I come up with for that, and this whole number are going to follow this math equation. So when I take this value here and subtract this value here from it, I come up with negative 149 joules per Kelvin. And that's because all these words mole cancel out. Okay? And if you look at that, what's my actual sign? If it's negative, that means it's going down in value for entropy because it's going this way on my number line, isn't it? So it's becoming more ordered or less random. Right? Remember that line back there? Okay? If I'm becoming less random or more ordered, it's a negative value. So that's what I found by doing my math. Now let's go back to enthalpy. There's 3 ways to solve enthalpy problems. You can use Hess's law, you can use heat of formation, or you can use bond dissociation energy. So let's do a Hess's law problem first. Alright, so let's look at this right here. Here I have 2 equations, and whenever you have Hess's law, you're always going to have equations. And so my job is to take this reaction right here, look at the equations they give me up here. They give me 2 equations. I'm going to take these 2 equations, and I'm going to go ahead and flip them around to find my values for my total reaction that I want to know, which is this one right here. People often do this in the real world because they don't know how much energy is going to be creative, and I want to make sure that I don't overheat my reaction vessel or I don't kill people, and I want to make sure that I have enough energy to run a reaction or enough energy to contain it. So if you look, I'm going to look at this reaction down here, and I'm going to look what I have. I have S as a reactant. So I come up to my equations, and I also have S as a reactant up here. So I'm going to leave this equation as is. So I'm going to copy it down and put 2S. And for this, guys, I'm going to forget about states of matter. And I'm literally going to go ahead and just copy this down. Alright, and because I'm not changing the direction of anything, I'm going to go ahead and put my delta H values here, and it's negative 790. I'm going to go ahead and label and put kilojoules up here. Okay? Now, the problem is that in my reaction that I want, I have 1 mole, and up here I have 2. So that means I need to divide this whole equation by 2, including my value here. Now, I've got my S. Now I need to look for my SO2. my SO2, right, I have my S right here. My SO2 is in this reaction up top, but it's on the wrong side of the arrow. So I need to make sure I be a good bookkeeper, and I'm going to take this reaction right here, and I'm going to completely flip it. So I'm going to put 2SO3 right here, and then I'm going to copy down 2SO2 plus O2. And because I'm flipping my reaction, I'm also going to flip my sign. So I'm going to put positive 196. Okay, now I'm going to end up dividing this by 2, and this is why. Because I have one SO2 here, and I have two SO2s here. So to get rid of that, I need to go ahead and divide everything by 2. The whole equation. Because look what happens. Isn't this now a 1? And isn't this a 1? And isn't this a 1 and this a 1? So now look what happens. SO3 is never mentioned in this reaction, right here, my overall reaction. And look what happens. What you start with and end up with never gets mentioned in a reaction, so it's not in the overall reaction. But now I have a problem. I only have one oxygen here. I have 3 halves here, and I have 1 half on this side. Well, if you look, this is the same thing on this side as 1.5. I can do my math. And this is 0.5. So if you start with 1.5 and you end up with 0.5, didn't you only use 1 in the first place? So that works. So you've solved the puzzle, and now all you need to do is your math. And so if I do my math, I end up with negative 395 kilojoules here, and 98 kilojoules here, and I'm adding this whole thing up. I'm adding this whole process up to equal my reaction right here. And so when I add negative 395 plus 98, I actually get negative 297 kilojoules per mole. And that's the answer to my problem. And in this case, it would be exothermic reaction. Now, what if you have this situation where you have a heat of formation? Heat of formation is how much energy it takes, how much heat it takes to form hydrogen chloride, hydrogen bromide, or bromine, or chlorine. If you notice in my problem, it tells me the standard heats of formation that they've looked up on a table, but it doesn't tell me the standard heat of formation for bromine or chlorine. And guess what? I don't need to include them. And the reason why I don't is because the heat of formation for an element is 0. Think about it. You don't walk around and waiting for people to make oxygen. You breathe it every day. It's already formed. But it took energy to make HCl. It took energy to make HBr. It takes energy to make compounds. So, here we are again. We're doing final minus initial, or products minus reactants. And in this case, I'm going to go ahead and put the sum of my products, which are 2 moles of HCl plus 1 mole of bromine. And my values that they give me in my equation for HCl are negative 92. So I can put negative 92 right here, kilojoules per mole. And this is going to be 0. And I'm going to multiply these two. So this basically goes away, doesn't it? Minus, what are my reactants? Well, my reactants are here. So I have 2 HBr moles, right? 2 moles of HBr. And the value for HBr up here is negative 36.4. I'm going to multiply those two, and that's kilojoules per mole. Plus what? Chlorine? 1 mole of chlorine. But guess what? The value for chlorine is 0 kilojoules per mole, so I'm going to forget about that. Now if you look, I should actually on this another color. Sorry, guys. I now have negative 184 kilojoules per mole minus a minus 72.8 when I do my math. And when I do negative 184 kilojoules per mole minus a minus 72.8, my value is negative 111.2 kilojoules per mole. And if I asked you what the overall enthalpy was, you would tell me that this is an exothermic reaction because you have a minus sign right here. So far we've done a Hess's law, which occurs when you have two or more equations and a final equation. A heat of formation, which happens when you have values given to you and you need to do this type of reaction right here, products minus reactants, just like we did when we did the entropy. And now we have another one, and this is called bond dissociation energy. And when you see bond dissociation energy, you get all excited. You see bond energy, you think, this is where I break bonds to make bonds. Okay, let me see if I put another page in here. Yes, I did. Okay, so I break bonds to make bonds. Is this true? Don't you have to snap all these bonds apart? I got OO, I got HH, I got to snap them all apart, mix them all around, and make two waters. Okay? So I break bonds to make bonds. I take what I break and I minus what I make. Don't memorize this with final minus initial, you get confused. So, what are my bonds I'm breaking? I have one oxygen right here. And the value for a double bond oxygen, which is what this is drawn like, is 495 kilojoules per mole. So, how many moles do I have? I have 1 mole of O2 times 495 kilojoules per mole. I'm starting with this. It's different from what we've done before, isn't it? That's because you're using bond energies. And the bad song that they sing is, you got to break bonds to make bonds. Okay? So here you go. I've got 1 mole of oxygen. And now I have 2 moles of hydrogen. What's the value for hydrogen? The value for a hydrogen single bond is 432 kilojoules per mole. Those are all my breaking bonds. I've taken care of my moles, 1 mole here and 2 moles here. Now I'm going to subtract the sum of the delta H's for the bonds formed. Look at water right here. In water, I have 1 OH bond here and 1 OH bond here. And I've got the value for only 1 OH bond here, so if you do this, I'm going to go ahead and say I've got 2 moles of OH bonds, don't I? Because I have 2 moles in 1 water molecule. But what do I have here? I have 2 moles here. So if I have 2 waters, don't I have this? So in reality, can I write 2 moles right here? No, I can't. I actually need to write the number 4. Because if I have 2 waters, 2 water molecules, I have 1, 2, 3, 4 bonds. So 4 moles of OH bonds times the value for 467 kilojoules per mole, which is the value for 1, I come up with positive 425 kilojoules per mole. This is 495. The value for this ends up being 864. And the value for this ends up being negative 934. And when you do your math, you come up with positive 425 kilojoules per mole, which means this is an endothermic reaction. So by the way, to solve any kind of problems, you can have Hess's law, which means I can have Hess's law for G, H, or S. Or I can use a table of thermochemical data and the formulas that are as follows: final minus initial, right? Products minus reactants. The only one that you run into when you do bonds broken and bonds formed is when you have bond dissociation energy. Okay? And you know that when you have bond dissociation energy and bond energy, you get all excited and you do break the bonds minus make the bonds. Alright, last order of business for the day is Gibbs Free Energy. And so let's look at the units. The units for delta G are kilojoules. Usually kilojoules per mole, right? Okay, the values for delta H are kilojoules. Again, usually kilojoules per mole, all right? They end up canceling out though. Temperature has got to be in Kelvin because the value for S, the units for S, are joule per Kelvin. And so you can see there's a problem right now because you have kilojoules here and kilojoules here and you have joules here. So when you write down the Gibbs Free Energy equation, you write it just like you see it in the black that's printed on the screen. But when you actually do your math, you do delta G equals delta H minus T delta S, and you throw a 1 over 1,000 there. Because that 1 over 1,000 takes care of changing joules to kilojoules. But you do not write it here when you write your equation on your paper. You only do it when you do the math. And that's exactly what we're going to do in a minute. But first, we need to talk about whether reactions are spontaneous or not. Now, if you look at this right here, delta G equals negative NFE. You learned when we did electrochem that E is positive and it's spontaneous. That means a reaction makes volts on its own. This equation is a known equation. There's a negative sign in here for a reason. This negative sign is in here because if this is positive and it's spontaneous, this ends up being negative. That means that delta G is spontaneous when it's negative. And you're going to have to memorize that. Remember it. Put it in your memory. Understand it. So if you look here, delta G is going to be spontaneous when it's negative. It's not going to be spontaneous when it's positive. And if I fill in values for H and S, if H is negative and S is positive, forget about the temperature, then delta G is always going to be negative. If this is positive, delta H is positive, and S is negative, this is always going to be positive. So when the signs are opposite, delta H matches delta G. That's what happens. Okay? Now, let's go down here. By the way, temperature doesn't matter. Let's go down and let's figure out what happens when you have the signs that are the same. So let's make the signs the same. If they're both negative or they're both positive, what's going to happen to delta G? Well, it depends. And that depends on the temperature. When you have a negative value for both of them, a low temperature is going to make this number right here a very small number. So when you subtract it, it's going to be a negative number over here. So when is delta G spontaneous? When the signs are the same for H and S, when temperatures are low. And I remember that because in a number line, a negative in a positive direction, negative is like a small number. So it's a low temperature, which makes delta G negative. If delta H and delta S are the same, then I need a high temperature. So when I subtract this, I'm going to have a big negative number, and that makes this a negative. So what's true there, this is high because if they're both positive, it's like it's a huge number. And so therefore I have a high temperature that makes this spontaneous. You need to memorize this chart and understand it. So when is delta G spontaneous? Always when delta H is negative. Never when delta H is positive, when the signs are opposite. When the signs are the same, temperature drives it. So these are only negative when both are negative at a low temperature and when both are positive at a high temperature. So question, what would happen if this changed and this went to a high temperature? Then this would not be spontaneous anymore. What would happen if you change this to a low temperature? Then this would not be spontaneous anymore. Okay? All right, now, let's go over here and let's do a problem. Okay? So, this is our last problem for the podcast. Gibbs Free Energy. To calculate delta G at 25 degrees Celsius for the following reaction, the first thing I know I got to do is I got to change this to Kelvin. And the reason why, because if I recall my equation of G, go, home, team, sports, that's in Kelvin. So 25 and 273, I'm going to have a nice value of 298 K. And so that's going to be my temperature value. Now, what don't I know? I want to find delta G. That means I need to find H, and I need to find S. Let's go ahead and do that. And I already have it set up here. I'm going to go ahead and go back to find delta H. I'm going to do my products minus reactants that I did before. And so the values for these are, negative 393.5 kilojoules per mole. The value for water is negative 241.8 kilojoules per mole. The value for this is negative 484.5 kilojoules per mole. And if you recall this is 0 because it's an element. So what am I going to do here? I'm going to take these and I'm going to multiply them and add them together with this, multiplying that. I'm going to take this and multiply these values and add it to my 0. And so when I come up with my numbers, I come with negative 1270.6 kilojoules per mole minus a minus 484.5, which gives me negative 786.1 kilojoules per mole. Oh, excuse me, just kilojoules, right? Because my moles cancel. Okay, so I'm going to include that mole there. And that is my value for delta H. So now what do I have to do? Now I've got to find delta S. And so my delta H value I have as negative 786.1 kilojoules. What do I need to do over here? Well, here I have my products minus reactants. Okay, and so my products, I've got 2 moles of carbon dioxide, which the value for that is 213.7. Okay, and that's joule per Kelvin mole. And my moles are going to cancel, right? I'm going to multiply these two. I need to take my value for water, which is 188.8 joules per Kelvin mole. And those are my products, aren't they? Right here. Now I'm going to go ahead and take my reactants. And what are my reactants? I have 1 mole of CH3CO2H plus 2 moles of O2. My value for this is positive 159.8, so I'm going to multiply those, joules per Kelvin mole. And my value for this is 205.1 joules per Kelvin mole. And so therefore, when I do my math, I'm going to end up with 805 minus 570. And my value for S is 235 joules per Kelvin. Now I have a problem. Remember my problem? My problem for S is that S is in joules. So when I put it back into my equation, I need to convert that. So what's my equation for this? Go, home, team, sports. And when I actually do my math, I'm going to put in my negative 786.1 kilojoules. Minus my temperature, which is 298 Kelvin, right? Then I'm going to have to take my S value, which is 235, right, joules per Kelvin. And I can do it on the side or I can do it here. I'm going to take 235 joules per Kelvin. I'm going to multiply it by 1 over 1,000 joules to kilojoules, which changes that to kilojoules. And look what happens. My Kelvin are going to cancel. My joules are going to cancel. I'm left with kilojoules. So when I do my math, my delta G is negative 856.1 kilojoules. That's my value for delta G. Now, question, is this spontaneous? If you said yes, you are correct, because it's a negative value. All right, and let's think if that makes sense or not. This was negative, wasn't delta H negative? And delta S is positive, and so you could have predicted by looking at the chart back here that indeed it would have been spontaneous, because if this is negative and this is positive, you get a negative delta G. So, I hope that helped. If not, you can email me. And I tell you this, good luck. Look over all your notes. And I'll see you on Tuesday or Wednesday.